Welcome back to Mr. Hassan's Maths channel. I'm now going to answer question number 7 from the Solomon L C4 collection. And this is a question that I've put in my Pure Mathematics P4 end of topic worksheet for vectors. And it's question 3 for my worksheet. The question has been requested by one of my students. So I'm going to be answering this question now. It says the line L1 passes through the points A and B, which with position vectors 3i plus 6j minus 8k and 8j minus 6k respectively, meaning in the same order. So A has the vector given first and B has a vector given second, relative to a fixed origin. So what they've basically told us here is that the vector from O to A is this first vector, and I'm going to write it in column form because it's much easier to deal with when you're doing calculations. So 3, 6 and minus 8. You don't have to write I, j and k because the top row is i's, then j's and then k's. And we also know the vector, the second vector is a position vector of b, meaning from O to b. That's what position vector means, from O to that point. So O to that vector means it's from O to b. Okay, so that's from O. So we have 0 i's and 8 j's and negative 6 k's. So we don't have to write the I, j's and k's, just write the numbers in the right places. Okay, so that's what we have so far. Now they've told us to find a vector equation for line 1. Now vector equations are very similar in a sense to normal equations of straight lines. Okay, so the vector equation of a straight line has two components. It has something that tells you about its position and something that tells you about its direction. So when you have a equation of a straight line in Cartesian form, is y equals mx plus c. C tells you a point on the line, which is the y-intercept, and m tells you the gradient of the line, which basically tells you in which direction it's going. If I know the gradient is 5, I know it's going like this. If the gradient is minus 5 or minus a half, I know it's going like this. You can see that the gradient tells you how much to rise and run between one point and another. Okay, so that's the Cartesian equation of a straight line. So we have the same thing in vector equations of a straight line. We have two components. We have one component which tells us a position on the line and another component that tells us a direction on that line. So we need to find the vector equation of line 1, and line 1 passes through the points A and B. So I'm going to draw a little diagram here. I'm going to show a line. Oops, I'll have it as a solid line. Okay, say that's the line L1. Okay, we've got three-dimensional vectors. We can't really draw it accurately because it's 3 dimensions. And we know that the line passes through A and B. So let's just say A is here, and let's just say B is here. Okay, so the line passes through the points A and B. Okay, to find a vector equation for this line, I need two things. I need a position vector of a point on the line. That gives me, somewhere to go to on the line. So from position vector is always from O. So I'm going to call this the point O over here. So that's the vector from O to A, which is our vector here, 3, 6, minus 8. That's a vector O to A. Let me put that a bit neater. Okay, so that's 3, 6, minus 8. 3, 6, minus 8. That's O to A. And we also have vector from O to B, which is given. This vector from O to B, that direction. It's 0, 8, and negative 6. That's the vector from O to B. So the vector equation of the line has two components. You have the first component, which is made up of a position of a point on the line. And we have 2 points on the line, the position vector of A and B. So I can use either of them. I'll just use the one for A, which is 3, 6, minus 8. So that's the first part of the vector equation line. It takes me from O to the line. So now I'm on the line. Then I've got to have a scalar. I'll call it lambda. You can call it st, call it whatever you want. It's just like a constant that changes depending where you want to go. And I need to be going along the line. So for example, when lambda is 1, if I have this vector as a direction of the line, if the direction is going in this direction here, then when lambda is 1, I might end up over there. When lambda is 2, I'll end up over there. So I'm starting from O to A. So I've got this vector takes me to the line, and this vector, if it's parallel to this line, it will take me along the line somewhere. So this will be a vector equation of the line because it will take me along the line and nowhere else. Okay, so the first part takes you to the line, and the second part, if it's parallel to the line, will take you somewhere along the line. So what I can do here is I can find the direction of this line, and that we can see the direction of this line. If I find the vector from A to B or B to A, it will be along this line. So let's try to find the vector from A to B. Now A to B, we can see the vector A to B. If I want to go from A to B, I've got to go from A to O and then from O to B. So it's like negative OA plus OB, which you could say is O to B minus O to A. That will take me from A to B. Okay. All right. So now I've got to do is I've got to take O to B, which is 0, 8 minus 6. And I've got to subtract from it vector O to A, which is 3, 6, and minus 8. So this is now the vector from A to B. So I'll write it down here. The vector from A to B is going to be minus 3. And you have 8 minus 6, which is 2. And you're going to have minus 6 plus 8, which is also 2. So this is the vector from A to B. And that's what I'm going to write down in this place here. Minus 3, 2, and 2. And this is the vector equation of line 1. Okay, so there we have it. That's part A done. The vector equation of line 1. We could have also put, it says A vector equation. I could have also put 0, 8 minus 6 here as a position vector. And I could have put this vector as a direction. I could have even put 3 minus 2 minus 2. That will also be along the line, but in the opposite direction, still parallel to the line. So it doesn't matter as long as I have a point on the line for my position vector and a direction of my line for this direction part, which is multiplied by the scalar. Those are valid equations of this straight line L1. Okay, so this is the equation of line L1. That's part A done. Now for part B. It says a line L2 has a vector equation given r equals minus 2i plus 10j plus 6k plus mu times 7a I minus 4j plus 6k, where mu is a scalar parameter. Show that the lines L1 and L2 meet. Now when these two lines meet, that means that there's going to be a point at which they meet. Okay, so if I equate the two equations of line 1 and line 2 together, okay, then I should be able to show that they intersect. So let's do this. Now we know that this is the equation of line 1. We just found it now. And what I'm going to do is I'm going to equate it to line 2. I'm going to equate it to line 2. So I'm going to say that's equal to line 2, which we know is minus 2, 10, 6, plus mu times, and we got 7, minus 4, and 6. So they're going to be some values of lambda and mu. There will be one value of lambda and mu for which these two must be equal to each other, because they have to meet at the same point. There's going to be a value of lambda that takes this to the same point as a value of mu which takes this to that same point. So let's just equate them together and make 3 equations from the I, j, and k components. Let's take at the top row. We're going to have 3 minus 3 lambda is equal to minus 2 plus 7 lambda. 7 mu, sorry. 7 mu on this side. We got 6 plus 2 lambda is equal to, we're going to have 10 minus 4 mu. That's the second equation. We have minus 8 plus 2 lambda again equals 6 plus 6 mu. So we have equation 1, equation 2, equation 3. Now what I'm going to do is I'm going to try to solve one pair of these equations simultaneously and find the value of lambda and mu. Okay, if that value of lambda and that value of mu causes the other equation, which I didn't use, to be satisfied, both sides being the same, that means I have found, I have proved that these two lines intersect, because I find a value of lambda and mu which satisfy all 3 equations, meaning that they will definitely intersect. Okay, so I think equation 2 and 3 are the best to use because they have the same number of lambdas. Okay, and we can eliminate the lambdas from there. Okay, the other ones, they're all different. Here the lambdas are the same. So if I use equation 2 and 3, let me do equation 3 minus equation 2. Equation 3, take away equation 2. Then I'll have minus 8 minus 6, which is minus 14. 2 minus 2, which is 0, which is what I wanted. 2 lambda minus lambda, 2 lambda is 0. Then I have 6 minus 10, which is negative 4. I have 6 minus 4, which is 10. So I have plus 10 mu. So if I rearrange this, I can add 4 to both sides. That'll be minus 10 equals 10 mu. So I can divide both sides by 10. So I end up saying mu is equal to minus 1. And mu is equal to minus 1. Let's find what lambda is. I can substitute this into any of these two equations. Let's choose equation 2. I'll have 6 plus 2 lambda equals 10 minus 4 times minus 1, which is plus 4. So I'll have 2 lambda equals 14 minus, that's going to be 14 minus 6. 14 minus 6 is 8. So lambda is equal to 4. So I know that mu is equal to 1 and lambda is equal to 4. Now I have to prove that these two satisfy equation 1. So let's take equation 1. We have the left-hand side of equation 1, and we have the right-hand side of equation 1. The left-hand side of equation 1 is 3 minus 3 lambda, and the right-hand side is minus 2 plus 7 mu. So let's substitute the values in. So for this one, you have lambda. So this is going to be 3 minus 3 times lambda, which is 4. That's 3 minus 12, which is minus 9. And the right-hand side, you have minus 2 plus 7 times mu. Mu is minus 1. Minus 2 minus 7, which is minus 9. So you have the left-hand side equals the right-hand side. So therefore, they intersect. They intersect because we found when lambda equals 4 and when mu equals minus 1, all three are satisfied. Okay, you can give a little reading if you want. All three equations were satisfied by those same values of lambda and mu. Okay, so that's part B. Now we're going to go on to part C. Okay, we're going to go on to part C. Okay, for part C, it says find the coordinates of the point where line 1 and line 2 intersect. This is the information I got from the last page. We know the equation of line 1 and the equation of line 2. We know the value of mu and lambda where they intersect. So all you need to do is to choose one of these two lines and put in the value of lambda or mu into them. So for example, if I use line 1, I can just replace the lambda with 4. So I'll have 3, 6, and minus 8 plus 4 times minus 3, 2, and 2. So I'll end up with 3 minus 12, which is minus 9. And I'll have 6 plus 8, which is 14. And I'll have minus 8 plus 8, which is 0. So that's the point. So we want the coordinates, so we write it in coordinate form. This is the position vector of the point where they intersect. And the coordinates will be given as minus 9, 14, and 0. And if you wanted to double check to make sure that you've done it right, we could just also try to put mu as minus 1 into this equation and see if this gives us, it should give us exactly the same point because that's when they intersect. So minus 2, 10, and 6. And you're going to have plus mu, which is minus 1, times 7, minus 4, and 6. Now that gives us minus 2 minus 7, which is minus 9, which works out. 10, this is a minus 4. So it's 10 minus 1 times minus 4 is plus 4. So it's 10 plus 4, which is 14. Okay, 10 plus 4, which is 14, which works out. And 6 minus 6, which is 0. So you see we get exactly the same 2 points. So we know for sure we're right now. This is the point at which they intersect. Okay, the coordinates, give it in coordinate form. Okay, then it says point C lies on line 2 and is such that AC is perpendicular to AB. So I've just written down a few things that we know from the first page that might help us. Okay, so it says point C lies on line 2 and is such that AC is perpendicular to AB. Okay, so I know a few things now from this question. I know that line L1 and line L2, they intersect somewhere. Okay, I even know the point where they intersect. Okay, and I know that point, say this is line 1, say this is the point A, and say this is the point B. Okay, it says the point C, AC, is perpendicular to AB. AC is perpendicular to AB. So it says the point C lies on line 2. So this is line 2. Okay, so point C is somewhere along line 2 such that AC is perpendicular to AB. So AC is perpendicular to AB. So C will be somewhere on this line such that when I join C to A, if I join C to A, that will be perpendicular to line 1. Okay, that's what it means here. Okay, so C is on this line too, and if I join it to point A, AC and AB will be perpendicular. Okay, right, so that's what we're saying. We have to find now the position vector of C. The position vector of C is going to be the vector from O to C. That's what it's going to be, the vector from O to C. Okay, let's say that's O, that's C. That's the vector they want. Okay, they want the position vector of C. This is from O to C. Okay, now, what we can do here is we can use the fact that AC, the vector from A to C, is perpendicular to the vector A to B. And I already know what A to B is, so I need to find what A to C is. Now, I don't know what A to C is. That's what I have to find, right? That's what I have to find. So let's call that vector X, Y, Z. O to C, no, let's call O to C X, Y, Z. We have to find, we have to find O to C in the question, but let's find what A to C is, because we need to use this information. So let's find what A to C is. We can find A to C using the fact that A to C is going to be found by doing A to O plus O to C, which is minus OA plus OC. So we can say that the vector from A to C is like going from A to O and then plus O to C. So it's like O to C minus O to A. Minus O to A. All right, and O to C, I've called it X, Y, Z because I don't know what it is, and that's what I have to find. So I'm going to call this X, Y, Z minus O to A. And O to A, we know is a vector 3, 6 minus 8. That was told to us in the beginning of the question. So I can say that the vector from A to C, therefore, can be given as X minus 3 and Y minus 6 and Z plus 8. This is like, in terms of X, Y, and Z, the vector from A to C. And I know that these two vectors are perpendicular. Now, perpendicular vectors have a dot product which is 0. So if I multiply AC and AB, so I've got my vector AB, which is minus 3, 2, 2. And I'll multiply that by vector AC. I'll have X minus 3 times Y minus 6 times Z plus 8. Now the dot product of those two must be 0. Whoops, must be 0. So I need to now, I can do that. That give me something. That will give me some equations now to deal with. The dot product of that is 0, so I can now multiply these out. So I can say so that will give us minus 3 times X minus 3 plus 2 times Y minus 6 plus 2 times Z plus 8. And all of that will give us 0. The dot product of these two must be 0 because these two are perpendicular to each other. Two perpendicular vectors, they have a dot product of 0. Okay, so that's, we get an equation from that. Now, we also know another piece of information that on line 2 lies the point C. So the coordinates of C, okay, which is X, Y, Z, are going to satisfy the equation of line 2. So there will be a value of mu for which point C, we'll be able to get to point C on line 2. That means if we take the equation of line 2, which is this equation here, so this is the equation of line 2, what we can do is we can equate this to the point that is XYZ, which is a point, this is like the position vector of C. There's going to be a value of mu that takes us to this point, same point XYZ, because C lies on line 2. So now what I'm going to do is I'm going to make 3 equations from that, and it's going to be minus 2 plus 7 mu equals X. So from this follows on that minus 2 plus 7 mu is equal to X, and also that 10 minus 4 mu is equal to Y, and then 6 plus 6 mu is equal to Z. So now I can combine these 3 equations together with this equation over here. I can now, solve them kind of, you can say, simultaneously. So I'm going to take my X in what I found in this equation and replace the x in the equation above with that, same with y, same with z, and I'll have one big equation with just mu's in it. And mu will be the only unknown. I can find that value of mu for which we're going to get to point C. So I'm going to do that now. I'm going to substitute inside this equation, okay, what x is equal to. I'll have minus 3 times, now x is minus 2 plus 7 mu. So if I put minus 2 plus 7 mu instead of the x, I'm going to get minus 5. Minus 2 minus 3 is minus 5 plus 7 mu. So I'll have 7 mu minus 5. And then if I put, instead of y, 10 minus 4 mu, I'll have plus 2 times. Now instead of y, I'm putting 10 minus 4 mu. So I'll have 10 minus 6, which is 4. 4 minus 4 mu. 4 minus 4 mu. And then I'm going to have plus 2 again times z plus 8. So instead of z, I'll put 6 plus 6 mu. So I have to add the 8 and the 6, gives me 14. And I'll have plus 6 mu. And all of that has to equal 0, because dot product of all that was 0. So now I can find what mu is by expanding this. So I have minus 21 mu plus 15 plus 8 minus 8 mu plus 28 and plus 12 mu equals 0. So you've got minus 21 and you're going to have plus 4. Minus 21 plus 4 mu is minus 17 mu, and you've got 15 plus 8, which is 23. 23 plus 28 is 51, so you have plus 51 equals 0. So we can see here that 17 mu is equal to 51, therefore mu is equal to 3. So when mu equals 3, we're going to get to line C. We're going to get to the point C on line 2. So we know the equation for line 2 is R equals minus 2, 10, 6, plus, now I know mu now is 3 where C is, so I'm going to put 3 in here. So I have 7 minus 4 and 6, and that will take us to the position of C. So I'm going to have minus 2 plus 21, which is 19, and 10 minus 12, which is minus 2, and 6 plus 18, which is 24. So this is the position vector of C. That's what we had to find. So we could say that the position vector of C, O to C, is given by this vector 19, minus 2, and 24. And there we have it. There's the answer to this question. Okay, so thank you for watching. Other questions from this paper, I'll put them in a playlist that should appear up here once I get around to doing some more questions from this Solomon L paper. Other questions from vectors in P4 you will find in this playlist that should appear somewhere over here. You can subscribe to my channel from the icon that will appear, and you would have seen a card during the video at the top here taking you to a P4 past paper for you to have a look at. Thank you for watching and see you soon.